Good morning. I guess we should start. Beginning to be a marathon of sorts. You're showing up every morning for the morning lectures. I think it's easier to stand here than sitting there listening to us, because we get caught in the excitement of what it is that we do. I'm going to talk to you about turbulence. Needless to say, this is probably the most outstanding and most difficult problem in classical physics. It's engaged many people who, after trying for a few years, moved on to other things, and some have endured and continue working on this problem. I'm going to talk to you about turbulence in fluids and space plasmas, but just to take a step back, yesterday we were talking about dynamos, and I just want you to pause and reflect on how there too turbulence plays an extremely important role. We all started out saying that we were just going to look at the induction equation, and we simplified the problem down from full MHD to the consideration of one equation first, which was the point of departure for our study. But soon enough, turbulence caught up with us. Even if we should start at a low level of fluctuation, a small seed, and a magnetic field grows, the fluctuations grow. And soon you have all the nonlinearity of MHD coming in, playing a very important role. So underlying the dynamo problem, there's the MHD turbulence problem. Not only that, in the dynamo problem, what we said was that not any kind of turbulence will do. If we have to have order emerge from disorder, it has to be turbulence of a special kind. So to just connect up what we are doing today in the context of what we did yesterday is that we implicitly did go into what kind of turbulence we would want in order for magnetic fields to emerge from chaos. It's really a very counterintuitive thing. We think of turbulence as chaos in general, but the dynamo problem was a step removed and was asking more of us, not just to describe that disorder. We first have to understand quantitatively, but also to figure out how from that disorder you could have order emerge in the form of a large-scale magnetic field. We are going back now into trying to understand the nature of turbulence itself, which is at the heart of so many things. And today, the dynamo for one, looking back, but moving forward, Professor Lee will talk to you today about acceleration and heating in the solar wind. And certainly turbulence is a very important mechanism for doing that. This is part of the reason why we study turbulence in this summer school. But turbulence is a very important problem in its own right, both for its fundamental physical content and also for its many applications. Moving away from the solar wind, planes fly, and we all know that there is a lot of turbulence that planes have to deal with. People haven't fully solved the problem of hydrodynamics turbulence, as I'll talk about today, but they do know how to design planes. And so computer modeling has played a very important role. Phenomenological models have also played a very important role. By phenomenological models, I mean models which make sense of observations, but have elements of theory in it. Perhaps not everything first principles, but parameterizing our understanding well enough that we can do things with it. Fusion plasmas still don't produce a reactor. They have turbulence in them. And I suspect that we will build a reactor before we solve the turbulence problem there too. So this problem has a long history. It's amazing why this problem is so very, very hard, and there are very many ways to get at it. But we'll just make very preliminary beginnings today. And once again, I'll start from the very basics, and I try to stay away from a lot of technical discussion, but emphasize ideas. But some of the mathematics is unavoidable, but I'll try to keep it at a minimal level. So going back to Webster, what is colloquial and what is understood by scientists. So Webster in 1913 describes turbulence as the quality or state of being turbulent. That's very helpful. A disturbed state, tumult, disorder, agitation. All of this you experience. And I think you use the word turbulence in more than one sense. But going to a mathematician, Alexander Chorin, lectures on turbulence theory, he makes a very important point, more precise. He says, the distinguishing feature of turbulent flow is that its velocity field appears to be random and varies unpredictably. The flow does, however, satisfy a set of equations which are not random. We'll talk about a bunch of these equations. This contrast is the source of much of what is interesting in turbulence theory. So we start from equations that are strictly deterministic, but the outcome of it is seemingly random, by which they mean is that suppose if I give you a set of deterministic equations and a set of initial conditions, just like Newton's law, you know the final answer. But if you change the initial conditions just a little bit, the answer will change. But for small changes in initial conditions, if there is a large change in the final answer, then you begin to think, I have deterministic equations, of course, but small change can give large variations. So if you think in a practical way, how precisely can we nail down the initial condition of a complex system? There are always small things that are different. Well, then those small changes can lead to very, very large changes in the final answer. This is what you will see in almost everything we do. We start from deterministic equations, but small changes in initial conditions make large differences to the final answer. This very character is true not just of fluid, but also of plasma turbulence. But at a basic level, this was the revolution of chaos theory in a way. Back in the 1970s or 80s, when people were beginning to realize that complexity does not mean that the degrees of freedom of the system have to be very, very large. Small number of degrees of freedom, billiard balls on a table, take 3. They go around. That's not an integrable system in the sense that small changes in the answer will make, in the initial conditions, can make big changes in the final trajectory of particles which collide. This was at the heart of chaos theory, which is why in 1980s or so, when I was a graduate student, there was a sense that if we understood chaos theory, we'll understand turbulence theory. Out of that line of work came out a lot of mathematical work, which is still very much in the literature. It gave us new insights, but never really solved the turbulence problem. Because the turbulence problem turned out to be more difficult, if I may say so, than the problem of chaos theory, which tried to reduce the turbulence to a bunch of simple differential equations that could be solved either analytically or on the computer or by constructing special maps or by doing little experiments. And undoubtedly, those reduced systems show complexity. Lorenz's butterfly effect is a very important example that all of you know about, right? Butterfly flaps its wings on one part of the hemisphere. It can make major changes in the other part of the hemisphere. It may seem like a joke, but it really is there in Lorenz's equations. So, but did it solve the turbulence problem? No. Nonetheless, what we learned from all of that exercise is this point that Chorin actually makes, is that a small change in initial conditions can make large changes in the final answer. Well, here's a picture from Leonardo da Vinci for those of you who've gone to Florence have seen this painting. He understood a lot of things. He was the quintessential Renaissance man who not only did painting, sculpture, science, engineering, you name it. So this picture of his, of large worlds and little worlds, is still our dominant picture of how turbulence develops in a fluid. You start a system creating vortical structures which are very large, and then over time they break up into smaller and smaller and smaller vortices. And these vortices keep going smaller and smaller until viscosity starts chewing them up. And this process of beginning to disturb the system at very large scales and then have the energy go from the very large vortices to intermediate sized vortices to vortices that are eventually dissipated away is the picture of turbulence that we will be pursuing, at least in the hydrodynamic case that we are about to talk about. Okay. So let's start with fluid turbulence. And for simplicity, density has been taken to be equal to unity, constant unity. So we won't worry about density anymore. You could multiply it by rho on the left-hand side, and you'd be fine. But we also assume incompressibility. So assuming that density is a constant from the continuity equation automatically gives you that. This is cast in dimensionless form, where R is the Reynolds number. L times typical velocity divided by viscosity. And viscosity is often indicated by the coefficient nu. It's called the Reynolds number. This is the single dimensionless quantity in hydrodynamics or fluids. So you can characterize the dynamical behavior of the system by giving a set of boundary conditions that will enable you to solve these equations. And this is a first order equation in time. You give it an initial condition and you integrate that. This term is the only nonlinear term in this equation. It's a product of V dot grad V and is responsible for all the notoriety of the turbulence problem. One term. This is what we've been doing for 200 years. Makes you feel humble indeed about how much people can actually understand. F here is the forcing function that can be 0. You can just create an initial condition and let it decay. That's what is called decaying turbulence. Or you could force it through external perturbations or the other. And this is the equation we're trying to understand. So you'll say, how do I calculate the pressure? Well, one way to calculate the pressure is to take the divergence of this equation. Del del T of del dot V would go away. And you'd have divergence of this term equals del square P on the right-hand side. This term will go to 0 because it's del dot V. And forget about F for the moment. Then you can solve for pressure if you know V. These two equations, in short, are all you need to know to calculate all the terms in the equation, V and P itself. Sometimes what people do is to get rid of the pressure by taking the curl of this equation and getting an equation for the vorticity. But that's just another trick. The pressure is very much there. It can be calculated a posteriori. So what does viscosity do? I'm going to take you to Feynman Lectures Volume 2. I don't know whether any of you have looked at Feynman Lectures. You must have as in your undergraduate years. And it has a very nice chapter on turbulence, actually. And there's an interesting story about Feynman. If you go back and read Michel Feynman's letters, Michel Feynman was Feynman's daughter and collected letters of Feynman. So she actually brings out all these letters and puts them all in a nice place, a very nice collection. So here is the history of Feynman's involvement with turbulence. This is what I read in that book. What happened was that Feynman got the Nobel Prize, and then he got this letter from one of his Japanese students writing to him, congratulating him on his Nobel Prize and telling him how great he has done in his life, doing these great problems, and then being very humble about himself, about what he is doing, not nearly as interesting as what you're doing. Feynman was a pretty busy person, but never one to pass up on a letter like that. So a few days later, he actually writes to the student back. He says to him that your letter made me happy and sad at the same time. Sad because I didn't really work on anything because I wanted to get the Nobel Prize. I worked on things that I had really fun with. And one of them happened to have gotten me the prize, and I had great ambivalence about even getting the prize. And proceeded to tell him about his experience with turbulence, that you probably do not know that I spent 2 years and more as a young man trying to solve the turbulence problem. And I did lots of algebra and even some computing and got nowhere with it. But he had high standards. Nowhere for him probably meant he went somewhere, but didn't really solve the problem. So he never really wrote up a single paper on any of this. But some of his notes eventually affected people like T.D. Lee and others who tried to do equilibrium statistical mechanics with Navier-Stokes equation, and also ran into trouble because this is not a problem that is tractable by equilibrium statistical mechanics. Be that as it may, what Feynman did leave us was this chapter in Feynman Lectures, which I urge you to read. And it's a very nice chapter. So what is the effect of viscosity? Experimental fact that's not at all obvious. The velocity of a viscous fluid is exactly 0 at the surface of a solid. Irrevocable fact. Example, the blade of a fan collects a thin layer of fine dust that persists even when the fan churns up air all around it. You've seen this, right? It's not hard for fans to collect dust. Turn on the switch and you look on. If you think the dust is going to fly off, simply because you're turning off the fan, it will spare you the exercise of having to get up with a duster and clean it. Good luck. Dust doesn't cooperate. It stays on the fan, even though the fan is churning, because strictly speaking, velocity is 0 right on the fan. What forces it to be 0? Viscosity. So air, just a little off the fan, is whirling around like crazy, but dust is stuck there. What does this mean? That means that near a wall, the velocity of a fluid can change rapidly from large values to 0. The narrow region where the velocity can change rapidly is called a boundary layer. And in the boundary layer, the effect of viscosity is very important. And I was talking to you about this yesterday when I was talking to you about the induction equation. But I didn't drive this point home well enough. But I want you to be aware of this, is that viscosity, which enters through R, multiplies, here you can tell me, let me give you the answer and I'll get back. It multiplies the term with the highest spatial derivative in the problem. Do you see that? Every other term has one spatial derivative. But 1 over R multiplies del square. Suppose I give you an equation. Epsilon x squared plus x minus 1 equals 0. Okay? Little algebraic equation. This is quadratic, right? You can solve this equation. Epsilon is a very small number. If you go to the limit of epsilon tending to 0 of that algebraic equation, what happens? What's the solution? I know it's early in the morning, but you guys are going to give me this answer. It's epsilon x squared. You can write this down. I have written it here. Epsilon is a small number. epsilon x squared plus x minus 1 equals 0. Epsilon is a very small number, 10 to the power minus 4, 10 to the power minus 5, whatever, take your favorite. 1. Okay. I was not trying to, but I'm going to ask you now, but how many roots does the quadratic have? So you went to the limit of epsilon going to 0 and you got 1 root, right? Okay. What happened to the other root? Yeah, something happened, right? That's very different. Yeah, some of you are giving me the answer already. That's very different than what would happen if I wrote the equation x squared plus epsilon x minus 1 equal to 0. But epsilon is multiplying not x squared, but the x term. So now if I ask you what's the result of epsilon going to 0, you'll say, oh, drop the middle term. X squared is equal to 1. You got 2 roots, plus or minus 1. So by taking the limit of epsilon going to 0, the naive limit, you haven't lost any roots. Those are approximate answers, no doubt. Plus or minus 1 is not, I mean, quadratic you can solve exactly. Whether I have epsilon here or epsilon there, there's a nice formula, right? You can solve it. So you know you're going to get 2 roots. But what changed between the first equation and the second is that in the first equation, epsilon was multiplying the highest order term. Hence, you lost a root. And I'm going to go back and recover the missing root in just a minute. But in the other algebraic equation, epsilon did not multiply the highest order, but the next order, and it didn't lose any roots. Big difference. So in mathematics, the first one is what is called singular perturbation theory, or an example of singular perturbation theory, because in the second problem, you can capture all the solutions by writing the solution as a power series. Powers of epsilon. 1 plus C1 epsilon plus C2 epsilon squared plus C3 epsilon cubed. And you can plug it into the second equation. And order by order, you can solve that problem. And you'll get corrections to the 2 roots, plus 1 and minus 1. Are you guys with me? Yeah? But in the other problem, that expansion fails. You know why it fails? Because what that misses is, so when you get x equals 1, you're essentially saying this term is small. And that's okay for that particular root. Sure enough, if you put, say, x equals 1 and you say, what's the next important correction? Well, if you plug in 1 there, that's order epsilon, which is smaller than the main root. But there is another solution for which epsilon squared is of the same order as x. So then you throw away this term and you balance epsilon squared plus x equals 0, and you get x equals minus 1 over epsilon. That root you would miss because you cannot get that. The leading order term is 1 over epsilon itself. That's the root that's heading off to infinity. And were you right in throwing away 1 in calculating this root? Well, if x equals minus 1 over epsilon, then this is 1 over epsilon squared. That's the largest term. This term is of order minus 1 over epsilon here. So this is the largest term you keep, balancing these two. And this is smaller. So this is a reasonable thing for us to do. So getting back now to this equation, what I want to emphasize is that 1 over r multiplying the second order derivative in the problem is a tricky business because you lose the derivative, the second order derivative in the problem, and anytime you do that, beware, because that means that you're missing something. You need to go and capture that solution, and you know the solution you'll be missing? You'll be missing the solution at the boundary layer itself, where the derivative itself is changing so rapidly that you cannot throw that term away, which is why even if you're multiplying it by 1 over r times del square, you're going to get a term which is of finite value. Why? That 1 over r is small, but the derivative can be very, very large in that narrow layer. So when you multiply the two, you get a term. So beware. So the lesson in all of this is that in turbulence, what you have is a separation of scales, and then there can be within turbulence itself, within a turbulent region itself, regions where the gradients are so sharp that even when they're multiplied by a small parameter, they actually produce terms that are important. So for some regions of turbulence, you can forget about it, but not everywhere. And so lots of fluid dynamical systems have all their turbulence near the wall of a container. And Feynman actually illustrates that through this sequence of illustrations here. So here he was, volume 2, there's a chapter near the end, and I copied his illustration of flow past a cylinder for various Reynolds number. Okay? So I'm going to describe to you a sequence of pictures, and I'm going to summarize it again in text. Here is flow. Now this R is not large. It's in fact 1 over 100, right? So that 1 over R sitting there, that's like 1 over 100. It's the opposite. It's not a large R at all. It goes from very small to very large R of fluid flowing past a cylinder. So these values, you have streamlines of the flow, and this is the solid cylinder. And you'll have a very narrow boundary layer near the walls itself. You raise the Reynolds number, you will see these structures, these vortex structures develop, which are still contained in these larger streamlines. When you exceed R and become 40 or higher, say of the order of 100, then you find that these trapped regions where these vortices were developing open up. And you form what are called vortex treats. Vortex rolls going down. This is actually a well-known terminology in laboratory vortex experiments. Yes. Please. It's less viscous. Because remember, R was UL over nu, where nu was the viscous coefficient. So you're becoming less and less viscous as things are going along. So this is forming, we are now at the vortex treat level. Then if you raise R even further, within these regions, these coherent structures, you start developing turbulence. Go further, these regions grow. They lose their coherent structures, and you get a trail of turbulence going forth. So we have implicit here is where, this is where the transition to turbulence approximately occurred. And by the way, this is well fortified by experiment. There are good theories for this, by which I mean theories which can describe when you have this sort of an instability developing in the system, and people do understand from the point of view of linear theory how these things come about, but certainly not the turbulent state. So let me summarize again in words what that picture showed. When R is much smaller than 1, the lines of V are curved, open lines, and constant in time. When R is in the range of 10 to 30, a pair of vortex structures develop behind the cylinder. The velocity, though more complex in space, is still a constant in time. So this is steady. In the very beginning, you have set things up, and you watch them in a camera. You won't see a lot of time dependence in the system. When R increases above 40, and you saw the picture for 100, the character of the flow changes. Vortices behind the cylinder get so long that they just break off and travel downstream, forming a so-called vortex treat. The velocity is no longer constant in time everywhere, but varies in a regular cyclic fashion. Go further and raise the Reynolds number. When R is increased further, that is, viscosity is lower, the vortex structures get trapped into the narrower regions, the boundary layers. Within these regions, the flow is rapidly varying in time. You saw that, right? It was largely coherent structures, but little coherent structures are filling up with noise, turbulence. When R increases even further, the turbulence works its way to the point that the velocity flow lines leave the cylinder. We have a turbulent boundary layer in which the velocity is very irregular and noisy. This velocity is a very sensitive function of the initial conditions. Small changes in initial conditions can produce very large changes in the final result. Velocity thus appears to be random or chaotic, although the underlying equations are not random. This closes the loop with Chorin's definition of turbulence, that you have a deterministic equation in which a small change in initial conditions, provided the Reynolds number of the flow is sufficiently high, would be nearly chaotic. On a computer, how will this show up? You will find that if you run the same simulation code with even changes in just initializing the code every time, because the random noise in the system, round off, is unpredictable. You will have an ensemble of realizations, each one looking different from the other, even though the differences between the initial conditions are extremely small. This is how you actually often produce an ensemble. Experimentalists do this by having very reproducible systems which they restart every time. Computer simulationists do it by rerunning their code and even having round-off error taking the place of different preparation. Both have been very, very valuable in understanding turbulence. Are you guys all with me so far? Okay, tell me when I begin to lose you, which I think I did eventually yesterday, as I gathered by talking to you. But as long as I get through most of it, I'll be pretty pleased. Some of the things that I don't get through to you doesn't get through to me either. I may be telling you this, but there may be questions about how well I understand it myself. Turbulence is a problem like that, as you will see near the end. We'll end up in confusion at the end. So spatial characteristics of this turbulence, you're seeing the turbulence couples large scales to small. Okay? The process of development of turbulence often starts out as large scale motion. You saw that in this example. By the excitation of waves of long wavelength that quickly produces waves of small wavelength by domino effect. By domino, I mean you're stirring this, right? But think of Leonardo da Vinci's painting as well. Large vortex structures, wavelengths of a certain K, then produce a shorter wavelength, and then a shorter wavelength. So if you think about it, you're going from small Ks to large Ks, or large lambda to small lambda, progressively. And there's a domino kind of an effect in hydrodynamics, because you're starting out with large worlds, which in turn produce slightly smaller worlds, and on you go, down and down the curve. Kolmogorov produced in 1941 what Uriel Frisch would tell you today is the only rigorous theory of turbulence. It's embarrassing, but he was a very astute mathematician and statistical analyst, and realized very quickly that solving that equation, Navier-Stokes equation, is going to be a hell of a mess. So what he chose to do is to make a bunch of bold hypotheses, which in some people's minds are nothing more than dimensional analysis. And by so doing, derived a result which just stood the test of time. We have tried to solve this original equation many, many ways on the computers, and we've also carried out many experiments, wind tunnel and otherwise. All of this stuff, but the large part, have confirmed Kolmogorov's spectrum, that in a turbulent flow, when you are setting up a turbulent system, you stir on the large scale and you form this domino effect, form an intermediate range where you excite all these wavelengths, and then the energy is dissipated in the region of large K. That region in between, the intermediate scale, is what is called the inertial range. And it is a range of wave numbers between the forcing scale at small wave number at large wavelength and the dissipation scale at large wave number, which is small wavelength. And he gave an argument that the energy is going to go like K to the minus 5/3, which is a universal spectrum for all these problems. Are you guys with me? So this was what his result was. And as I said, it stood the test of time. Now, in Uriel Frisch's book, which I strongly recommend to you, it's a great book on turbulence, he codifies Kolmogorov's assumptions in very formal language. And I'm going to give you a very simplified version really, in Kolmogorov's, after all that is said and done, rigor notwithstanding, the argument is really as simple as this. So what he said was, okay, so you have this turbulent system where you stir in the large scale, keep on stirring. Cream and coffee, our favorite example. Put cream in, stir with a spoon. That's stirring on the large scales. Well, stirring on the large wavelength, you're eventually going to tie into smaller and smaller wavelengths, and the energy is going to be distributed according to some law. He wanted to determine that law. And he said he was going to make certain assumptions, namely that the turbulence depends only on the magnitude of K, not its direction. That was the assumption of isotropy. Okay? E, in 3 dimensions, K is a vector. But he argued, no, it will depend only on the magnitude of K. You will see that this strong assumption will be violated when we go to magnetized plasmas in a way that we have woken up to only, I would say, about 20 years now. And he also said that the interactions are local in K space. What he meant by that was simply that if you have a large eddy, it breaks up into an eddy of smaller size, and the interaction that occurs is only between eddies of roughly comparable wavelengths. As the energy goes down to one of smaller wavelength, it will create in turn additional smaller wavelengths and so on and so forth. But the interaction is not going to be between the largest structure and the smallest, but always between neighboring eddies of similar sizes. So all interaction in wave number space can be done sort of locally in K space. Those were his basic assumptions. And he said that in a steady state system, there's going to be a steady cascade rate, energy per unit mass, per unit time, that is going to go from one K shell to another. And that rate would be a steady rate and would be a constant in the entire inertial range. Are you with me? So these are very strong assumptions, as you will see. So this is what his cascade rate is, epsilon K. And then he argued essentially that it depends on only 2 parameters, K itself and the energy spectrum. Raise them to power alpha, this one to power alpha and this one to power beta, and these 2 quantities should conspire to produce an epsilon K, which is constant. Are you guys with me? Right? You got only 2 quantities. What is E of K? E of K is the total energy of the system. Just integrate over all of K space. Well, can you determine alpha and beta? This is actually a simple exercise. Yes. Essentially, the rate, yes, but the fact that it has, so you're absolutely right, that's the assumption of cascade rate. But you have only 2 quantities of K and E that depends on it. So how would you do dimensional analysis there? Well, let's do a little dimensional analysis. E of K is the energy, right? Per unit mass, by the way. So that's why you don't have a rho. So you use your favorite system. That's length square. Force, energy is force times distance, right? So what is force? Ma, right? M is 1. A is length by t square, right? But you have another distance coming in because energy is work. Work is force times distance. So you have m squared by s squared. With me? Cascade rate is the energy per unit time. So it requires another unit of time. And K is simply inverse length. All right. So E of K is just, you can write this down, m cubed by s. So dimensional analysis, you can show very easily that epsilon raised to the power 2/3 and K raised to the power minus 5/3 is what you need. That gives you E of K going like epsilon 2/3 K to the minus 5/3 with a constant C, which is not determined by dimensional analysis, and it's a universal constant. And this is Kolmogorov's law, where k is, in fact, the wavelength. Sorry, I wrote this as a kappa. It should be a k. So getting back, then, using simple dimensional analysis, you determine that alpha is 5/2 and beta is 3/2. And you invert that, that's the result you get. Experiments, both in the laboratory and in computer experiments, have determined that this is universal constant, varies typically between 1.4 and 2. So by using two major assumptions, without solving the main equations, Kolmogorov predicted that the turbulence of neutral fluids must have this universal behavior scaling like k to the minus 5/3. What have we done since then to reproduce these results? What people have done is done tons of simulations, tons of experiments, and even tried to solve these equations analytically. Because of the nonlinear term, let me say in one word that it's a hard problem. And people have tried to use various approximation schemes, what are known as closure theories. Direct interaction approximation due to Kreutzmann is one of the more successful approximation theories. With assumptions, it did derive this result, but it has been shown that those closure theories have their own problems. So to this day, we do not have a completely satisfactory analytical derivation beginning with the Navier-Stokes equation of this scaling law. Question? Okay, but you have to be a little bit careful about this because epsilon k is quantitatively constant, but it has a k dependency. So you want not to lose that while you're doing that, right? So you can actually say quantitatively for every say that you can combine this whole and it will be a constant for a particular inertial range. I'm not disagreeing with you on that. And this is k to the minus 5/3. So if you simply say that for a given experiment, Ek is proportional to k to the minus 5/3, you're absolutely right. And that's what people typically verify. I'm just making it more explicit because the epsilon k has a physical meaning in this context, that it has an implicit k dependence, which you can also calculate by simply saying if E of k is given, I can invert this relation and obtain how epsilon k goes. So it's all contained in the same relation. But you're absolutely right. Given a particular setup, the law is minus 5/3. Okay. So what's the observational evidence? Well, I'm now going to go, I'm not showing you a lot of hydrodynamic experiments. I'm now gradually going to make a transition into plasma physics or space plasmas or astrophysical plasmas. Remember, these are rarely neutral fluids. I know astrophysicists thought for a long time that they can understand the universe purely on the basis of hydrodynamics without any magnetic fields or plasma complications, but interstellar medium is permeated with magnetic fields. Go on. Question, anytime, yeah. Why that value in the inertial range only? Because it made no appeal whatsoever to any viscous dissipation loss or anything. So it's like energy coming in at the forcing scale and taken out. But you can ask me, what sets that scale where you take the energy out? Well, you balance the energy coming in with the viscous loss, and that sets for you what is called the Kolmogorov scale, which is actually dependent on the viscosity. As long as I am between the stirring scale and that Kolmogorov scale, viscosity plays no role, and this argument works. But when I step out of this range, then the scaling law changes, and it's no longer a simple power law even. That's true. It'll go down, it'll be dissipated in that range. Yes, yeah. Oh, there's energy conservation also in that. There are inviscid by, I mean, if you have viscosity equal to 0, then you get certain conservation laws that are actually valid in that range. Yes? That's the velocity. The viscosity in the system has a molecular explanation. So it's like friction, you know. And can I give a molecular picture of how you get viscosity in the system? Dragging a fluid on a surface, I won't be able to, let me tell you what I will give you a feel for, a qualitative picture that something is there as a drag. As to how it ends up being nu del square V would take more doing than I am going to do right now. So if you have a fluid and you get near the boundary, the molecular attraction between what constitutes the fluid and what is in the material of the wall is a frictional drag in the system. In an ideal system, we typically take that to be zero.
It's not dependent on the...
No, no, you're absolutely right. I was actually giving, so even fluid surrounded by another fluid layer, as long as there is a velocity shear, would experience this force. And you actually raise a really good question, because I gave to understand so far that all the boundary layers as if were near the wall. But there can be boundary layers developing in regions of strong velocity gradients, even within a fluid itself. It doesn't have to be a metallic boundary wall itself. In plasma physics, actually, such boundary layers occur far away from walls or confining systems because of the properties of the equations themselves. So you're absolutely right, there can be internal boundary layers in a fluid as well. And I was just oversimplifying. Okay. That is determined by viscosity. And in fact, the smaller nu is, the narrower that layer is, and sharper the gradients become in a treatment of the boundary layer. Like the gradient operator I was telling you about in these equations, that will scale like 1 over nu to the alpha, some power typically. As nu, no, I misspoke. Gradient will scale like that, but the width of the layer will scale like nu to the alpha itself. So it'll get narrower and narrower, and the gradients get sharper and sharper. That's why nu del square can become a term of other unity. Even though the width of the layer is shrinking, the gradients are becoming larger and larger. Yeah. Yeah. You could define such a thing where there's a local, sure, and oftentimes people do that they actually use velocities that are more characteristic of what is going on, close to the boundary layer. You know, just before you step into the region itself, there's sort of an outer limit of the inner layer, if you will, where people use that velocity. So let me, remember now the interstellar medium has magnetic field in it. Let's go to the solar wind. This goes from Goldstein and Roberts. They're confirming, this is done in a frequency domain, and there is a particular thing in satellites that allows you to go from frequency to wave number using a so-called Taylor hypothesis. I won't go into those details here. Just to let you know, this being used interchangeably here. Look, minus 5/3. But the big question is, why is it that Kolmogorov's law that we derived for neutral fluids is carrying over to a magnetized plasma? Why should the same scaling law hold? In fact, you know, this was not the first measurement of this. The earliest measurement of this in solar wind was due to Lee and Jacobi, who made this point that you have Kolmogorov spectra. And you know, Kolmogorov spectrum is so successful in fluid dynamics that we inherit the whole thing over and we say, yeah, that's great. But why? You've got magnetic fields, right? What do magnetic fields typically do? They produce alpha waves in systems. They produce a whole bunch of other waves in the system. Let's take the simplest wave that we have, the alpha wave, which depends on the magnetic field. Kolmogorov did not make any allowances for the presence of magnetic field. He was fine. He was solving hydrodynamic turbulence. Why should we be happy with k minus 5/3, knowing fully well the solar wind turbulence has magnetic field in it, and this has no dependence on it whatsoever? Why should this law work? But it does work. So then we should ask ourselves the question, can we derive this law from the MHD equations rather than the hydrodynamic equations? Okay, seems like a reasonable challenge. Are you guys with me? So if I asked you to reconstruct a theory of MHT turbulence, how will you change Kolmogorov's argument? That's the point I made, that between frequency and wave number, I'm going to use that interchangeably because actually there's something called Taylor's hypothesis that enables you to do that. I won't dwell on that. You're right, I'm using frequency here, but allow me to do that for the moment. Imagine that omega and k have some proportionality with them, and this is a separate technical discussion that would be too much of a digression for me at this point. Is that okay? Just allow me, just think of that as essentially a wave number kind of a thing. So you have k 5/3 again. So now my question back to you, how would you fix Kolmogorov's theory? If I tell you that there is a whole bunch of alpha waves running around, what would you want to do to Kolmogorov's argument to get a scaling law? The most naive thing you can do, kind of thing I would do. I'm going to say, give you a hint, right? Things dependent somehow on k and E of k. And then we did dimensional analysis with it. Now I have put in a new ingredient, alpha waves. How do you want to fix that? How do you want to take that into account in Kolmogorov's argument? Take a random guess. You want to try dimensional analysis? Will you be successful? Okay. Let's try it. The problem is, so just fixing Kolmogorov, believe it or not, Krishnan did just that. But he quickly realized, well, there was a k and E of k, right? You remember that. So he said, well, this is a sea of alpha waves. So I'm just going to put in alpha waves and additional dependency. That has a dependency on the magnetic field. Raise it to the power gamma. Redo Kolmogorov, now with the dimensional analysis. The problem is with alpha and beta, see, Kolmogorov was a very clever guy. He had two coefficients, and there was as many equations as unknowns. So you could calculate alpha and beta. If you put in a gamma, gamma is underdetermined from this one equation. So you end up getting a relation like alpha equals 5 minus gamma over 2 and beta equals 3 minus gamma over 2. But what is gamma cannot be determined by dimensional analysis alone. You have to put in more physics in there to figure out what gamma is. Well, if gamma is 0, you get back your Kolmogorov result. Turns out that Iroshnikov and Krishnan found that gamma is -1. I'll tell you how. But they didn't do so out of pure dimensional analysis itself, because there are just not enough equations. Written as the epsilon k equals k ek, if you just put in the dimension of k and the dimension of E of k and the dimension of epsilon, you have two equations, two unknowns. You determine alpha uniquely. Alpha is 5/2 and beta is 3/2. But when you put in the gamma, there's just not enough equations and unknowns. So you have to put in more physics. We will do that physics right after a 5-minute break. Maybe you'll figure it out in the break, okay? So, and then we'll come back and derive this Iroshnikov-Krishnan's scaling law, and notice what is happening. The spectrum has changed from k to the -5/3 to -3/2. VA is entering the problem as you expect it to through magnetic fields. And how we get to that result we'll do soon after. Take a break. Thank you. Sure.
The first one is about the picture showed on the Feynman's lecture. So with as a Reynolds number increase, so the viscosity actually decrease, right? And then the flow develop into the turbulent status, right? So my understanding is like, what's the energy dissipation when the Reynolds number is very small? So it's like when the viscosity
It's very dominant, you mean?
right. It's like when the viscosity decrease, the flow develop into that turbulent status to dissipate the energy more.
is what I call now. Okay. Okay, so I want to we have a little unfinished exercise yet to determine what that exponent is. I gave you the answer on what the spectrum is going to be, but I'm going to lead you up to the ideas that give you that. But before the dimensional analysis part, it helps to take a step back. Since dimensional analysis didn't give us an answer, and we know we have to look into the physics underlying what's going on, it's good to contrast hydrodynamic turbulence with MHT turbulence. And so, as I was telling you, hydrodynamics turbulence is an interaction of various eddies. What happens in MHT turbulence is that imagine you have a uniform magnetic field in the background, and it's a very simple system, uniform magnetic field. You can solve the MHT equations, and what you find is you get alpha waves propagating either up or down the magnetic field. Turns out that alpha waves are solutions not only of the linear MHT equations, but also of the nonlinear MHT equations. So these are exact solutions of MHT equations. Put in a uniform magnetic field, put in an alpha wave, you can show that the nonlinear equations are satisfied exactly. So an alpha wave propagating in one direction by itself just keeps its form. There can be another alpha wave propagating in the opposite direction. Alpha waves propagating in the same direction do not interact. The only way in which you would get turbulence occurring in an alpha wave system is if you have waves propagating on opposite directions, and then they collide. And this is a very important defining property of alpha wave turbulence. This can be made more precise mathematically by actually defining what are called Elsasser variables. And this is nothing very fancy, but it also, this bit of mathematics also makes the physics more transparent, is that if you start with the MHT equations and take the J cross B term and you rewrite it, you can write it as two terms, a gradient of B square over 8 pi and a B dot grad B term. But that B square over 8 pi you can absorb with the pressure, and let's call it a new pressure, which is a thermal pressure plus the magnetic pressure. I'm just not writing it for the sake of simplicity, that's all, okay? Now, you can take the uniform magnetic field that I have, write it as a B0 plus a fluctuation, and these are Elsasser variables. Elsasser was a person who did some really nice work on MHT. Among other gifts to the community, he was also the postdoctoral mentor of Eugene Parker, who did a lot of great work in solar physics, as you know. So Elsasser pointed out that these equations in the incompressible case can be manipulated into a very nice nifty form in terms of Elsasser variables, which are z plus or minus, v plus or minus, the Alfvén speed essentially. Okay? And this you can get, and I won't do the algebra, by just simply linear combination of this equation and the induction equation. Write this out as del V del T. You can write this one out too. Then you add and subtract, you'll get these equations. Okay? And look at this, is a very curious equation. Here is plus propagating. Look at this nonlinear term. It has a product of z minus and z plus. Similarly, the equation for z minus has a product of z plus and z minus. What does that mean? That if in fact z minus were 0, z plus would never know anything about z minus. By itself, it just propagates merrily along until it hits a z minus when you get a nonlinear interaction. But if there is no z minus in the system, there's no nonlinear term. Similarly here, this is just another way of saying the picture that I just said to you before, that Alfvén waves propagate as coherent structures nonlinearly parallel to a magnetic field, and they interact only when oppositely propagating Alfvén waves hit each other. When they do hit each other, what happens to them is this picture, z plus coming this way, z minus going the other way. They interact and they perturb each other. Okay? So all of MHT turbulence theory can now be done in terms of these Elsasser variables. And people find it technically a simplification. It's also physically quite transparent because of this mixed nonlinearity I was telling you about, z plus z minus, z minus z plus. So you can see that the major source of disturbance of a propagating Alfvén wave is when it interacts with an Alfvén wave propagating the other way. Keep this in mind very, very much. Without this, there is no MHT turbulence. If MHT turbulence consisted only of Alfvén waves propagating in one direction, you'll never see an MHT turbulence. And this, in fact, raised some questions about solar wind turbulence for a long time before it was resolved. Now, in the original system, we had conservation laws. Energy of the flow and the magnetic field energy and what is called cross helicity. When you write things in terms of z plus and z minus, these things can be combined to produce new invariants, E plus and E minus, and invariants only on the inviscid system. So these are only invariants that are valid in what I was telling you was the inertial range, where dissipation is not playing a role, not the stirring range or the dissipative range. And when E plus is of the same order as E minus, you have what is called an energy balanced case, where there's as much energy in Alfvén wave propagating in one direction as the other. Many cases of great interest, particularly in the solar wind, and you'll see why I'm saying this, Alfvén waves in one direction and the other are not necessarily balanced, they're imbalanced. Because look at the solar corona and energy coming out of it. There's a hell of a lot more energy that actually goes out than comes in. You can ask yourself, and this actually did pose some problems, because if you looked at the work of Belcher and Davis, going back, Belcher and Davis, this is taken from the data, I forget, was it Ulysses or Voyager? Voyager, I think, right? Somebody will correct me, but this was classic work that made Belcher and Davis very famous. Look at three components of the fluctuating magnetic field and velocity field. They're being measured, and they're perfectly aligned with each other. The characteristic property of an Alfvén wave is, as you know, V scales like B. Forget about the extra factor of square root of 4 pi rho. And by looking at these observations, Belcher and Davis said, you have an enormous number of Alfvén waves, but notice these are all V parallel to B, V not anti-parallel to B yet. But if turbulent cascade has to rely on waves propagating in both directions, it's not totally obvious from this study where the oppositely propagating alpha n waves are coming from. People worried about this, but there was no denying that when you looked at the sun's heliosphere or the heliospheric current sheet, that probes were measuring energy spectra of the kind that I showed you. Jacobi Lee did that, and Goldstein and others did that. They were measuring energy spectra. So where was this oppositely propagating alpha n waves coming from? You guys get the question, right? Think of ways in which you may be generating oppositely propagating alpha n waves. Yeah. Yeah. Exactly. So as I said, the dispersion relation has a rho dependence and things like that, but that means that when alpha n waves propagate, density stratification in the system can produce a ways of producing oppositely propagating alpha n waves. In fact, in the heliospheric current sheet where the shears are great, density variations are significant, you can get a lot of these kinds of oppositely propagating waves occurring for more than one reason. And so people therefore came to live with the fact that they are getting spectra and oppositely propagating alpha n waves. So now that we have this, we can go back and try to get so we know that alpha n waves are good building blocks and that collisions of alpha n waves are tremendously important. So now I'm going to give you a simple heuristic estimate on how to get the energy spectrum right. Remember that gamma we have to determine, and we knew the dimensional analysis didn't give us the gamma, so we need to go into the physics of interaction of the alpha n wave. So here is your z minus and here is your z plus. Think of two wave packets, each of length L approximately, that are propagating. So ZL at t plus tau a can be expanded, ZL of t plus tau a times del ZL del t. But this is ZL of t tau a, and this is simply written as a scaling law of ZL over t, t being a typical time scale. The deformation of the wave packet after one collision then is given by this quantity, tau a ZL square over L. Great. Now this deformation will grow in time and you will have many such collisions happening because all these alpha n waves are randomly distributed and they're colliding with each other. It's like a random walk of a drunken man, Brownian motion. How does it go? Like the square root of the number of collisions, roughly speaking, right? That's what Brownian walk arguments are. And how many of these collisions we are having? Each one of them lasts roughly a tau a, t over tau a square root. So we take a sum of all of these, many such collisions occurring between the waves. So let's proceed with the argument. You have a cumulative distortion of order 1, which is defined as the sum of these adding up to a typical amplitude, and that's given by this number. This then gives you an interaction time of tau tau r. Just invert this relation given by this quantity, which is tau square AD by tau a, L over UL being the typical interaction time of an eddy. This is the kind of interaction that you had Kolmogorov's ideas in the first place, but now in the presence of the magnetic field, the interaction time is actually modified by the extent of this quantity. In the presence of strong magnetic fields, these interaction times can be very short. You can calculate now the energy spectrum going like ZL square tau square by tau a. This is the time taken. Divide out and you get this result, E square k cube by B0, from which you get the Hiroshnikov-Kreisman spectrum going like k to the minus 3/2. This is what enabled us to determine the gamma that we were talking about. Well, I already showed you a lot of data on k to the minus 5/3, but between 5/3, which is 1.66, and 3/2, 1.5, there isn't a whole lot of difference. In fact, Marty was just telling me over the break, do you think Jacobi and Lee tried too hard to get the 5/3 scaling law within the error bar? And they undoubtedly did. Because if you looked at the error bars of their measurements, it would be questionable whether you could get the 1.66 or 1/2. But error bars have gone down since that time. Here is measurements by Podesta, more recent. He reports both scaling laws for magnetic, in incompressible MHD turbulence. According to theory, magnetic and velocity are all the same spectral law. Nature is not so obliging. When you get it all down, what you find is the magnetic spectrum is 1.66, the velocity spectrum is 1.5. They're separated from each other. And I have gone through this with Podesta many, many times, and with many others, people by his observations. The error bars are sufficiently small that the fudge cannot be made, that this is a 1.6 by some way or 1.2 by the other. So if you ask me, what's the spectral law in MHD turbulence? It's not universal, not as universal as we made it appear. If you depend, the first question is, where do you get the scaling law, in velocity or magnetic fields? Then, where do you get the scaling law is equally important. If you get it very close to the sun, you get one set of scaling laws. Let the turbulence evolve out, the power changes. There is no good theory at the present time that explains why the answer is one or the other. So this is, in fact, a critical point of MHD turbulence theory, because we have two scaling laws, 3/2 and 5/3, that are seen in observations. And I'll submit to you in the rest of my talk that there are theoretical arguments in support of either 3/2 or 5/3. But let me get to that. Lee. That's definitely a possibility. In other words, we have so far considered only incompressible plasmas and shear Alfvén waves. These are finite beta systems where there are sound waves and other things as well. And the question is, does compressibility play a role? Does this change the spectral law? How good is incompressible MHD turbulence as a model for solar wind turbulence? All good questions. So it's entirely possible. But I want to tell you also something else too. The problems of solar wind turbulence are deeper than where MHD theory leaves you with. I've been telling you about the dissipation range, right? But in a collisionless plasma out there, viscosity is a negligible, classical viscosity is a negligible dissipative quantity. What comes in a lot before that, and these are experimental observations. This is taken by Sarawi, for example, using cluster data. Here you get 5/3, all right, in his data. But look at the break in the curve. Your different scaling laws begin, and what happens in these, and this is accepted by all solar wind observers and theorists of the solar wind community, that the break in the curve for the inertial range measurement, be it 5/3 or 3/2, does not occur at the value given by classical viscosity, but by the ion Larmor radius or ion cyclotron radius. And how do they measure this? They know the density, they can actually track it. The break in the curve actually occurs at typically at sub-ion scales. So there is an ion range, and in fact there is an electron range, and that the power laws in this range, if they are power laws at all, are very different than what they are in the so-called inertial range, be that 5/3 or 3/2. Now, about this, I'm going to leave you totally in a mystery today, because that would require that I abandon the MHD model altogether and go into kinetic theory. There's a whole industry of this going on right now in the field that I won't have time to get into, but it's really good for you to know what are the principles we bring to bear on this problem. So Kolmogorov's original framework of having a stirring scale, an inertial range scale, and a dissipation scale still stands. The stirring is done by the sun, say. The inertial range is what you have over very large decade range that you're seeing in the measurements. But then that stops after a while when you hit ion and electron scales, not a true viscous scale. And for the theory of that, it's still a growing line of work. In fact, it's not even clear that this is a power law. It could be exponential. It could be set by instrumental artifacts. You have to be very, very careful in separating out what a power law is from what is an exponential curve. And when the K range shrinks, it's possible to make mistakes, but theoretically and computationally. Now, this is a picture that Marty Lee had Christy Donahue, our UNH artist, draw that I've stolen. And if he was planning to show it to you, I want to just set the context of why am I studying turbulence, this totally intractable problem, in the context of the sun, is because you have these Alfvén waves coming out. okay? And then there is wave reflection, like he said, that gives you oppositely propagating alpha n wave. So you know you're getting MHD turbulence. Alpha n wave is an interaction between various wave numbers, okay? And you get all this coupling and turbulence going on, and then this actually produces wave-particle interactions at a kinetic level that heats ions and electrons. In fact, the nature of the turbulence deviates from being purely MHD-like to becoming kinetic in a way that is beyond the scope of this lecture. But this is the place that we are all living in, and the further and further out you go, the turbulence spectra actually evolves in space and time, and you see different exponents. Is this confusing or what? Well, it is. And there's a lot to be sorted out, and this is what we are in the process of doing. Now, I gave you a derivation of Krichnan's k to the minus 3/2 scaling law. But there was a very important thing that Krichnan left out. He was a great turbulence theorist, and he did know about this, which is that if you put in a magnetic field in a system, it is a source of very major anisotropy in the system. Structures, remember Kolmogorov's assumption was that E of k vector depends only on the magnitude of k. But who says in the presence of a magnetic field that the dependence would only depend on k itself? Because it is clear that the structures parallel to a magnetic field are going to be rather different. They're going to have wavelengths that are long, and wavelengths along the magnetic field, and wavelengths that are smaller, perpendicular to the magnetic field. In other words, E, which is a function of k, need not be a function of k only. In a system like that, it can depend on k parallel and k perp. Because if you go back and look at the shear alpha in dispersion relation, it's omega equals k parallel VA, where k parallel is the wavelength parallel to the magnetic field. Why should the spectrum not respect this dependency? This was the fundamental question that Goldreich and Sridhar posed for MHD turbulence. And if you go back and read Krichnan's work, he did in fact footnote it, and he said the assumption of isotropy in MHD turbulence is a vastly simplifying assumption and probably not valid. But he didn't do the follow-up work following that. And here is a simulation of Jim Stone's, my colleague at Princeton, of an MHD turbulent fluid, okay, which has a very, very weak magnetic field. It looks like a turbulent mess, right? But look what happens if he cranks up the magnetic field. You develop these cigar-type structures, which are oriented parallel to the magnetic field, long wavelength parallel and short wavelength perpendicular. So now we have another complication. We went from k to the minus 5/3 to k to the minus 3/2. We look at data. Data gives us mixed support for both. But even the data is oversimplistic. And the theory is oversimplistic because it's not discriminating between k parallel and k perp. Distinguishing between k parallel and k perp in data is very hard because you must have multiple satellites which are sampling. And Tim Horbury and others in UK have done a heroic job trying to separate out k parallel and k perp. And this is now new work. A lot of other people have done it so. And so they have now gone back and tried to check on the validity of these theories, taking into account the difference between k parallel and k perp. Well, what really happens is that if you go back and write your Elsasser variables and you do some careful analysis, you will find that this term scales like k parallel VA. Like I was telling you, this is a linear term. This is the term that gives you a shear alpha n wave. This is a nonlinear term, and the nonlinear interactions happen in the perpendicular directions. Now, when this term is very dominant over this, turbulence is weak. And when this is comparable, turbulence is strong. Most of the turbulence in nature is strong turbulence. Weak turbulence does occur under certain controlled conditions, but it has a general tendency to steepen up just as a function of time as you go. So only in rather controlled numerical experiments you can do this. And let me just tell you that there are certain things that promote anisotropy, which is that, Remember this picture I was showing you with different k numbers interacting? The simplest form of interactions that occur is called three-wave interactions. And one of the mistakes that Goldreich made in his first paper with MHD turbulence is that he did the weak turbulence theory first, and he actually argued that three-wave interactions are unimportant for MHD turbulence. And I remember I was in a workshop on dynamo theories, and I was giving a talk, and I had not read the Goldreich-Sridhar papers. So he came up to me and said, well, did you read my papers on MHD turbulence? And I was very embarrassed, and I said, no, I hadn't seen it. So he gave me the references. And the first paper was one on weak MHD turbulence, and the second one was on strong MHD turbulence. So I started reading them because I thought I really should understand this problem of anisotropy because it affects the dynamo problem. Well, take the weak turbulence paper, and the first thing he says is, Kristian theory is wrong because Kristian relied on isotropy, which he shouldn't have, and on that Goldreich was right. And then he said, Kristian also said the three-wave interactions are very important, and they are not. I was really stunned by the second assertion, so I remember doing some calculations on the plane, and when I got back, I did with a wonderful postdoctoral colleague, Chung Sang Ngun, and I said, Chung Sang, there's something wrong with this paper because it says three-wave interactions are empty. Well, I was just doing simple arguments like this. This is frequency matching between a third wave which is produced because two waves interact, counterpropagating alpha n waves. And if you do that, you show very simply that K1z or K2z must be 0 because this gives you Kz equals K1z plus K2z plus or minus, and this because of the modulus sign gives you only plus. The solution to both equations is simply that either this has to be 0 or that has to be 0, which meant that three-wave interactions are important, but they will not put any energy in the parallel direction at all. So if two alpha n waves interact, all the energy in the weak turbulence limit gets out in the perpendicular limit. So we wrote a paper showing how important three-wave turbulence is, three-wave interactions are, and how it sets up the anisotropic cascade. And other people too have done that, Montgomery and Matthews and others. So we redid the weak turbulence theory, and we essentially found that in the weak turbulence theory, this produces this result where the parallel and perpendicular neatly decouple, and I won't go into the analysis, but I'll show you the numerical result. Roughly what it comes to is, we're plotting E k perp multiplied by k perp 2, and you see this straight line? This tells you that E k perp itself scales like k perp to the minus 2. This is what happens in weak turbulence. So now you have two scaling laws now, one in the limit of weak turbulence, which is of more limited validity, and then another one for strong turbulence, which actually now has two possibilities. One is the strong turbulence theory of Goldreich and Sridhar, which was done correctly with three-wave interactions. The only mistake was that he argued the three-wave interactions don't matter in weak MHD turbulence. So weak turbulence theory was wrong, but the strong turbulence theory was right. And that theory gave k perp to the minus 3/2. Boulder, on the other hand, on the basis of a lot of numerical simulations and otherwise argued, this result of Goldreich-Sridhar needs to be modified further. That according to him, and these are complicated technical arguments that I won't have the time to go into, but I feel you're entitled to the facts. Because if I go into the details of all the arguments that went into Goldreich-Sridhar and Boulder, it will take another hour and a half to do that. But let me just give you the results. That the strong turbulence has two theories right now, both of which have evidence supporting them numerically. You can ask me this question, how is it that people can't get their computer simulations right to figure out whether this scaling or that scaling is right? Just as in experiments, it's very hard to do controlled simulations. The box size matters, how you set up the alphanic turbulence matters, and all these differences do produce differences in spectral laws. And people argue forever, which one is the right setup for nature? Yeah. Exactly. So you're asking, and let's have a good discussion on that. and maybe we'll have it during the break or in the follow-up to the lecture, because I'm running a little late. I apologize for that. But this is where we really are, that we have two scaling laws, which one is due to Goldreich and Sridhar. And here is the measurements, okay? This is one set of measurements, very high resolution, 2048 cube, done in a cube box with a uniform magnetic field, highly resolved. You're saying K-pop to the 3/2. Peter Goldreich has done his own simulations with his own postdoctoral fellows and students, sometimes with K-pop to the 3/2. People like Lazarian, Vishniak, and others have gotten K-pop 5/3. This continues to be a controversy in the community. Along with that, we have, of course, the real solar wind. This is clustered data that I was showing you. MHD turbulence, if you think this is f to the minus 5/3, this is what Saravi measured. K-pop 5/3. And then you have this regime where kinetic effects come in. And I was telling you, the first break in the curve comes at the ion skin depth or the ion Lama radius, depending on what type of systems you're dealing in. And the scaling law here, see the sequences of scaling law, he finds that there is a dominant alpha that lies between 3.1 and 2.5. Why is that? And this is where the electron scale is. So the classic picture is, at least in the Saravi paper right now, is that you have stirring going on the large scale. As long as you're in the large scale and above this dissipation range, you get 5/3 or 3/2. Then begins your dissipation range, which may or may not be the heating range. Dissipation only because this is where ion and electron kinetics is beginning to play a role. You're beginning to get different scaling laws. But where does the heating actually occur? Does it occur because the ions get heated up here? Or is it that the energy propagates all the way from the inertial range through this range and gets damped through Landau damping on the electrons? What gets heated? Is it the ions, the electrons? What are the waves that mediate the heating processes? There are MHT-like shear Alfvén waves on the large scale, but if you go down further, there are Whistlers, there are kinetic Alfvén waves. How important are these waves? Or are they sound waves, like Lee was suggesting, well beyond anything in incompressible MHD? Sound waves are Landau damped. Is it the effects of compressibility coming in and taking energy away and producing these sorts of scaling laws? These are all open questions. Sorry we're in such a mess. But thank you. Yes, we need the talents to solve all these problems in theory as in observations. And we need spacecraft, which will actually resolve all these things. And another, when you get to such small scales, you have to be very careful about what your instruments are telling you. There are cutoffs, right? Because instruments have instrumental limits on how far they can go. So if you see something exponential, is it because the instrument is playing a role in giving you exponential? Or is it that there is a proxy power law that you can catch somehow near the limit of your instrumental resolution? Open questions. Thank you all. It's a huge journey, and we are just partially through. Okay, let's take 5 minutes for any questions that you have, and then I don't want to steal time from your coffee break. Questions? Yeah. Okay, so there is, in fact, let me go back to that slide, which I went through a little bit too fast. Thank you for asking the question. It gives me a time to clarify. There is this dimensionless parameter that is implicit in what I just wrote. K parallel VA by K perp VK, let me write that parameter, gives you a way to control the size of the turbulence. And that's what is called a critical balance parameter. Really, it's the inverse of that, sorry. In the very beginning, as the turbulence, as the two Alfvén waves interact, you get a little bit of K perp structure. So that dimensionless parameter, K perp VK by K parallel VA, initially is much smaller than 1. Then, as the turbulence strengthens, K-pop becomes stronger and stronger, that parameter rises. When it hits the value of 1, you transition from weak to strong turbulence. And people have done controlled simulations. In particular, the person who has done this is Boulder with Perez and others. Perez is a postdoctoral fellow at University of New Hampshire, and now he has moved to Quran. So, and Ben Chandran also has done some of this work. You actually can show that in a system that you go from the weak to strong turbulence regime and the scaling law changes. And in Boulder's work, it goes from K-pop to the -2 to K-pop to the -3/2. But there are others who have different results. This we must get to the bottom of. This, I think, is a solvable problem. You know how it is sometimes you do a theory, two people do a theory, and then they defend it strongly. And the longer they disagree, the stronger they get entrenched in their own ideas and unable to see. It's a very human endeavor, physics. So we've come to the point where we've had these groups compare their results, and we still don't have a resolution of this issue. We should, and I'm pretty sure we will. There are some who would argue that Bolderev's point is very compelling, that really it's not K-pop -5/3, even though tempting it would be to say that's the correct theory, that incompressible emitted turbulence essentially leaves you with a Relishnikov-Krishnan scaling, with the K in Relishnikov-Krishnan just converted to K-perp. Weak turbulence is different. Nobody disagrees on our results of K-perp to the -2. That's well settled. Unfortunately, weak turbulence is of limited applicability. The solar wind is not weak turbulence, it's strong turbulence. So that we cannot use the K-pop -2 law there. And there the preponderance of observations is -5/3, but then you have these Podesta observations telling you velocity magnetic fields are decoupled. One has 5/3, the other has 3/2. And furthermore, the mystery deepens. As you evolve further and further away from the sun, that spectral index changes. You tell me. More spatially evolved turbulence, wait a long time for solar wind-driven turbulence to settle down to a scaling law which would be unique. How far is far enough? So on and so forth. Any other? Thank you very much. It's been a real pleasure. I'm sure I've failed in multiple levels, because this comes a point when I'm just giving you information but not telling you why it is so. That's all we can do. Thank you.